Hey guys, Jared here, and here we go with the uh, video for simple harmonic motion, gravitation, and circular motion. So, I don't have any questions yet for homework or anything, but what I'm going to do is just kind of start with circular motion and then work our way towards gravitation, and then from there go to simple harmonic motion. Um, so let's start with circular motion. So when an object is moving in a circle, we have to have some force directed in towards the center there. So again, circle, and let's say that this is a circular track, and I've got a car, say right here. Okay. Now, at any given instant, that car has a velocity that is tangent to the path that it's taking. So let's say we're going around at a constant speed. Well, if we're going around at a constant speed, then it's important to note the difference between on the actual road isn't some mysterious force directed in towards the center. It's the frictional force between the tires and the road itself. So I don't know about you guys, but coming home today during this, blizzard, I was thinking, oh, static friction, please hang in there, because that's what allows you to have control over your car. It's static friction. Once you have kinetic friction, that's when you are actually sliding across the road. So there's actual movement, skidding, if you will, across the road. And generally not good when you're talking about icy conditions. So let's say that this isn't an icy road. We've got a coefficient of static friction of 1. And I want to know How about now? 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 Okay, can everyone hear me now? Jeez. Thought I'd have that fixed, and I even got a reverb again. Okay. So, in case you're just tuning in, or in case you can just now hear me, we're working a problem right here where we've got a car, we've got a track with a radius of 20 meters, we've got a coefficient of static friction of 1, and I'm wanting to know with what velocity can I take that turn. So again, oftentimes the key is figuring out, okay, what is the static frictional force? So here we're looking at this from a bird's eye view. So we're looking at it as if we're looking down on the track and that car is going around in a circle. So it's that static frictional force coming in that, okay. Can everybody hear me now? Hang on, I'm getting, this is so fun because it's like you guys are updating me on how untech savvy I am. Let's see. How about now? Is this good? We feel good about this? Okay. So, okay, again, the key to these problems is looking at, okay, what is the static frictional force? In this case, what is the centripetal force? In this case, it is static friction. Well, from here, once you have what the centripetal force is, well, then just start substituting in the equations for both sides. So centripetal force is MAC. And static frictional force, the only equation we have for static friction is mu s times Fn. Okay, well, the question is to find velocity. Well, where can we get velocity? Well, velocity is in centripetal acceleration. Now, I'm going to break down the right side as m times v squared over r. And then over here, I'm going to keep mu s, but I'm going to break apart Fn as mg. Now, since we're on a flat track, that normal force is just going to be equal to the weight of the car. So if you notice, I didn't give you mass, but oftentimes if they don't give it to you, you don't need it. Mass is on both sides, so it cancels. So solving for velocity, I'd multiply both sides by r, so that would give me mu s times g times r, and that's equal to v squared. So the last thing I have to do is just square root both sides. Now, let's plug in our values that we've got. Mu s is just 1, gravity is 10, and r is 20. So this gives me 200 equals v squared. So your last step is just to square root both sides. The key to this problem is right here. Just writing out, okay, what is the centripetal force? In this case, it was static friction. Now, what if we've got a scenario where the centripetal force isn't necessarily static friction? It might be a little bit more complicated. So let's look at a planetary motion here for a second. So I've got my sun here in the center. I've got my planet out here. Let's put him at 1/5. No, let's put him at 200. And let's give ourselves a velocity of, I'm thinking we're going to need like 65 on this. Again, we want this to be in a nice, neat circle. Oh, drat, it's an ellipse. So in order to get circular motion from this, I'm going to lower my mass down just a little bit. So in order to get circular motion, I didn't have enough velocity, so I just ended up with that elliptical orbit. So I've got to up the ante a little bit. So let's start at 120 and see how we go from there. Okay, now too much velocity. So let's reset and go to 100 and try that. And, oh, yes. Okay. So here I have a circular orbit for the most part. It's nearly circular. I've got a little shortness here on this side, but this is probably truer to an actual orbit. Now, what's the centripetal force here? Well, if I stop it at any given moment, the force between these two objects is the force due to gravity. So, gravitation section, the force due to gravity, whenever you're close to the surface, is just mg. So whenever you're close to the surface of a planet, it's just your mass times the gravity at that particular section. But whenever you get further out from that planet, whenever you get out past that sort of realm, g is no longer g anymore. G is lowered as you keep going out, because the force due to gravity is now given as g m1 m2 all over r squared, where g is your universal gravitational constant. Now, g for our universe is 6.67 times 10 to the negative 11th, but again, that's just for our universe. Now, whenever you're working a problem like this, oftentimes there's a really popular multiple choice question, and it looks something like this. So they'll say that, on Earth, a person has a weight that is, I don't know, let's do 500. So 500 newtons, that's their weight on Earth. And they might say, okay, you go to this new planet, we'll call it planet X. So FGX. You want to know the weight on that planet. And they'll give you the relationship between two planets. So let's say here's Earth, and then here's planet X. It's really big. Okay, it's got a larger radius. So let's say that it has a radius of planet X is, let's say it's 4 times that of Earth. Okay, so it's 4 the radius of the Earth. But let's say that planet X, the mass of planet X, is the same as that of Earth's. Okay, so I've dramatically increased the radius of my planet, but my mass hasn't changed. So what do your instincts tell you about the weight on this new planet X? Do you think your weight, you've only got 3 options. It's either going to increase, decrease, or remain the same. Now, the only way your weight could remain the same if none of these variables changed. Okay, well, one of these variables, one of the masses, is the mass of you. Well, that's not going to change unless you have a kind of rocky flight to planet X. What does change, though, is this R value. So up top, my masses don't change, but my radius gets a lot bigger. It gets 4 times as big. which means weight is going to go way down. So let's actually figure out what our weight would be just knowing this relationship. So here's how you go about this problem. Write out what your weight on Earth would be. So Fg on Earth, well, that would be G, the mass of the Earth, and then times the mass of you. So my, my mass, over the radius of the Earth squared. So that's my weight on Earth. Now, my weight on planet X. Write it out what it would be. Well, okay, so I've got equals G, and then its mass is the same as the mass of Earth, so I'll just write mass of Earth. And then my mass also didn't change, so my. Now, here's where we get a difference, because it's over 4 times the radius of the Earth squared. Now, it's that whole term squared on the bottom, which means that I'm going to have 1 over 4 squared. So I've got 1 over 16 times, okay, so times G, the mass of the Earth, and then times the mass of me, all over the radius of the Earth squared. Well, this term right here, G, mass of Earth, mass of me over radius of the Earth squared, that's the same right there, which is right there, which is, FGX, right there. So this term is your weight on the Earth, which is 500. So your weight on planet X would be 500 divided by 16. So the trick to these problems, to these types of questions, is making one term look like the other. Okay, so make one equation look like the other. Get one equation, get the one for FGX, get it in terms of everything that's in FGE, the weight of the Earth. Okay, let's try another one. Let's say that on Earth you have a weight. Let's say again you have the same weight, 500. Okay, but now you go to a planet that let's say FGX. We want to know new planet X, planet X1. Okay. Well, planet X1, if this is the Earth, planet X1 is not only smaller, but it has more mass. So here's planet X. The mass of planet X is twice that of Earth's, and its radius, the radius of X, is half of what Earth's is. Okay, so I'm going to give you a minute to work on that, and then I'll come back and fill you in on the answer. Okay, be right back. Okay, so here we go. Your weight on planet X. Hang on, I'm having some technical difficulties here. Okay, there we go. So your weight on planet X. Well, again, it's going to be G, and then the mass of the Earth is going to be, or excuse me, the mass of planet X is twice that of Earth. So I've got 2 me. Now, my mass didn't change. And then I've got a radius on planet X of half that of Earth. So that 1/2 term gets squared also. So here we go. The 2 can come out right over there. And then I've got 1/2 squared, which is 1/4. So I get 2g, mass of the Earth, and then my mass. And then I'm dividing by 1/4 the radius of the Earth squared. Well, dividing by 1/4 is like multiplying by 4. So again, I factor out all the numbers and I'm left with just g, mass of Earth, my mass over the radius of the Earth squared. So if I take that 4 and bring it up top, I end up with 8g me my over re squared, which is my weight on Earth, which means I would end up actually weighing 4 times as much on planet X as opposed to Earth. So 8 times 500. So those are very popular free response style questions when it comes to weight, and it's not just limited to the it's not just limited to gravity. It can be pendulums or springs or stuff like that. So let's do another example of this style of question. Let's do it with a circular motion format. So let's say that I've got an object moving in a circle with a certain radius. Okay, call it r, a certain velocity v, and a certain centripetal force at just Fc. Okay, now let's say that I move the object out so that I am now at a new position that is twice as far. Okay, so now I'm at a position 2r, but my Fc stayed the same. Okay, so my Fc stays what it was before. Well, if I move out to a new distance and that doesn't change, that means that I have to have some new velocity. Now, what that new velocity would be, we have to look at up here. So let's say up here, Fc is ma, and a is v squared over r. Well, down here at this new position, well, I'm going to have some new velocity. I'll call it v2. Well, Fc stays the same, but now I'm at this new velocity v2 squared all over, well, now it's 2r. So it's tempting to say, okay, I go out to twice the distance, well, I'm going to have now half the velocity. Well, it's not quite the case. Now keep in mind, this FC is the same as this FC, which is that. So let's take this term, and let's plug it in down here. Let's figure out how these two velocities are related to each other. So I've got mv squared over r equal to mv2 squared over 2r. Well, mass is on both sides, so that cancels. And if I multiply both sides by r, well, my r cancels too. So my r's are gone. So it leaves me with v squared equals v2 squared divided by 2. So let's figure out how v2 is related to my initial velocity, v. So multiply both sides by 2. I end up with 2v squared equals v2 squared, my velocity at that new position. Well, if I take the square root of both sides, that tells me that v2 is equal to square root 2 times v. Now, square root 2 times v, that gives me a different velocity at that position. And so if I take the square root of 2, I end up with 1.414 la 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 la. So think about, let's say up here I was moving with a velocity of 10. Well, here out at this new distance, I'm moving with a much higher velocity. So this stayed the same. This r increased, which means my velocity also had to increase in order for it to be the same centripetal force. So think about like a merry-go-round. You go out further and further, well, your radius increases, you're going to be moving faster. You better hope that you've got enough static friction to keep you on that merry-go-round. Otherwise, not going to be good. Okay. So let's look at another problem, and let's kind of switch gears and go to pendulums. We're going to come back to gravitation and circular motion, but I want to kind of switch gears for a second and go to pendulums and springs. So if I look at a pendulum, and again, we're going to make sure there's no friction, and let's go ahead and show the energy of this pendulum. And again, we saw that if I change the mass of the pendulum, it doesn't really change my period. And again, period, if this thing is tracing it out right now, period is the time necessary to complete one full swing. So if I start the clock right here, I'm going to end it right there. Now what this program does is it starts it in the middle, it swings back, and then it comes back through. And that's the period of motion. So one full swing. Now, what does affect the period isn't the mass, but it's the length of the pendulum and the gravity acting on the pendulum, that restoring force. So if I dial down the length, if I cut the length in half, so I make my length 1 as opposed to 2, I'll bring it out to the same angle. I think it was 12 degrees before, and then start my period. Well, here we go. My period is now 2.01 as opposed to 2.8. So I cut my length in half, but I didn't necessarily cut my time in half. Now, check out over here this energy oscillation back and forth. At the top, at this amplitude of motion here, I have maximum potential. At the bottom, I have max kinetic and no potential. So we'll go back to the bottom here in just a second. So at the bottom, that is where I am moving the fastest. Now, if you're thinking about a pendulum and its motion, at the bottom, you have the fastest motion, which means you have the maximum kinetic energy. Now, a pendulum traces out really part of a circle. So at the bottom, we can consider that to be circular motion. So I have gravity coming down, Fg, and I have tension coming up, Ft. Now, my centripetal force, here, it's not just tension, because gravity is also directed along the center line. So centripetal force is really what's left over directed towards the center. Well, that's going to be Ft minus mg. Now, centripetal force is still equal to mass times centripetal acceleration. So if I take Ft minus mg, and I set that equal to my centripetal acceleration, which is mv squared over r. Well, r really is the length, which doesn't change really ever. The length of the pendulum remains constant. But what does increase at that bottommost point is that velocity. Now, mass doesn't change, gravity doesn't change. If this term goes up, that term has to go up also, which means you have maximum tension at that bottom point. Now, to figure what that would be, you might be asked to determine how fast that pendulum is going at the bottom, which means you could use conservation of energy. If you knew what height you started, you know that you don't have any velocity up here at this apex. In other words, if I release it from up there, my initial velocity is 0. So I could do k1 plus u1 plus the work done, but we're going to neglect friction on the pendulum, so let's just go ahead and cross that off right now, equals k2 plus u2. Now, if I think about the bottom and the top, well, at the top I have no kinetic energy, because again, this side would be the top or the amplitude position, and at the bottom, that's at the equilibrium position. Well, I have no final potential. So this term is mgh, and that's going to be equal to my kinetic energy, which is 1/2 mv squared. Now, mass on both sides, so it cancels out. And then gh, you can solve for velocity. And we've seen this before several times. We've got 2gh, and then we take the square root equals velocity. We've seen that quite a few times. And that's the speed that the pendulum would have at the bottom. So you can see that you can increase that speed if you draw that pendulum up higher and higher and higher. Now, in order for a pendulum to actually behave nicely, that theta has to generally be less than 30 degrees. But for our intents and purposes, all of our pendulums are going to be perfect. Now, what if I decided that I wanted to alter a pendulum? Let's say that I have a pendulum that has a certain length L and a certain period T. And I take that pendulum and I cut its length in half. So now my length of the new pendulum, I'll call this pendulum L1, its length is half of what it was before. Well, what does that do to the period of this pendulum? Does it increase it, decrease it? Does it remain unchanged? Well, period for a pendulum is related to, or is, 2 pi times the square root of L over G, the length of that pendulum and gravity. And we did this whenever we linearized that data. You know, we squared both sides, so we got TP squared equal to 4 pi squared times, if I square this, then that just becomes L, and G is a constant, so I'm going to put it right here, and I'm going to group those constants together. Y equals mx. Okay, but what we've done is I've cut this length in half. So up here, this pendulum, its period is just T equals 2 pi times the square root of L over G. And this pendulum down here with half the length, well, its period is the same thing. It's 2 pi times its length. But its length is 1/2 L. So that would be like L over 2 times 1 over g, so I can just put it there like that. Well, again, just like with gravity, you want to get this equation to look like this equation. And it's so close. It's 2 pi L over g, and here I've got this annoying 1 over 2 term in here. So what I can do, because all of these terms inside this radical are multiplied together, I can actually factor out that 1 over square root 2. So that's what I'm going to do. I'm going to factor out 1 over 2, the square root of 1/2, and then times 2 pi, and then times the square root of, capital L over g. I got it. I got this equation to look just like this one. So this term is right there. Oops, sorry about that previous equation. So that means that this term is our original period. So T1 is, again, the square root of 1 is 1. So 1 divided by square root 2 times my previous period, T, which means that my period is shorter, because we just said square root 2 was 1.4, so 1 divided by 1.4 is going to give me a decimal, which means that period goes down. So if I decrease length, well, period and length are directly related, so if I decrease length, I also decrease that period. And we can see that with our simulator here. So if I make length, again, let's get in real time here. If I make length really short and start my period, well, now I'm at 1.4 as opposed to 2. And if I make the length way longer and then start my timer, whoa, the period just crawls. It's way longer than it was before. And again, getting the equations in terms of the other will help you out tremendously with particularly multiple choice questions. Okay, let's switch gears one more time and let's talk springs. Now, we worked with this simulation some, and I'm going to go ahead and make my friction none. And what was cool about springs is that gravity did not affect the period of oscillation. So I can change my gravity to anything else, and if I get my stopwatch out, I start my timer. I'm going to slow it down a little bit. And if I start it at the top and then stop it here at the top, I end up with a certain period. And if I change gravity from 0 to Earth and start my timer, it's going to be pretty close to what it was before. Now, I was probably off by a little bit in the previous timing. So gravity doesn't affect the period of a spring. What does affect the period of a spring is how much mass is attached and the spring constant. So 2 pi times the square root of m over k. So just like with a pendulum, if I increase how much mass is attached, I'm going to increase the time. If I increase the spring constant, I'm going to actually decrease the time, because these two things are inversely related. Okay, now, just like before, we can do the same thing with these springs. So you can have a spring with a certain period, and let's say that if I have a mass m and a spring constant k, I have a certain period that it's just t. Well, now let's have a new spring, and let's say that it has a mass m2, and m2 is 3 times the previous mass. But my spring constant for this spring, K2, is 9, no, it is 27 times what the previous spring was. Okay, so I'm going to give you just a minute and look at this, get this bottom spring's period, its period, and I want how it's related to the previous spring. So it's got a spring constant that's 27 times the original, and it's got a mass that's 3 times the original. And how does that period change? Okay, so let's knock this out. Here we go. So the period for this spring would still be, losing my, there we go. So it would still be 2 pi times the square root of m over k. Well, our mass is 3 times what it was previously, and our k is 27 times what it was previously. Oh, look at that, 3 over 27, or 1 divided by 9. So my period, if I factor out that square root of 1 divided by 9, well, square root of 1 divided by 9 times 2 pi times the square root, well, I factored out this 3 over 27, so that leaves me with just m over k. Well, square root of 1 over 9 is really, square root of 1 is 1 and square root of 9 is 3, so this is 1/3. Now, I've got this 1/3 term, and then I've got 2 pi m over k. Well, this spring up here, its period is 2 pi times the square root of m over k. So I've got my T2 in terms of my original period. So T2 would be 1/3 that of my original period. In other words, this mass is oscillating much faster. So even though it's got more mass, my spring constant is 27 times as large, which means my spring is having much more force act on that block than before. Because of that, it's oscillating at a much greater rate. And we can see that with our springs here. So if I get this oscillating and I make the spring more rigid, it starts to, okay, so I make the spring more rigid and I let it go, and I get it in real time. Okay, it's oscillating very quickly. Now, if I make the spring softer, in other words, if I decrease that spring constant, and let's just keep the same mass on there, it's going to oscillate at a much lower rate than before. So in the example that I just did, you had low mass, so let's get the period here. Let's say it is right there, and then right there, so 0.7. Now, I tripled the mass that was attached. So 50 times 3 would be 150. Oh, bollocks. Why wouldn't you put a 150 mass on there? Can I add 2? No. Well, handy. So I've doubled the mass. Let's dial up our spring constant. Okay, and then attach our mass, let it go, and then boop, and then boop. So pretty close to almost half. So I made my spring constant much harder, not very accurate up here, and I doubled my mass. Okay, so in this last little bit, I want to talk about kind of the whole big picture together. So I'm going to talk about what we've talked about with energy and gravitation and gravitational potential energy. That's what I want to finish this section up with, this video up with. It would probably be a pretty good idea to really hone in and pay attention on this last bit, if you catch my drift. So let's look at a solar system, but let's make it a little less circular. Let's make it a little bit more elliptical. So let's put that at 50. Let's see how we do. And excellent. Okay, so we don't enter the sun, so our planet's not dead. So awesome. Now, if you look right here at this section closest to the sun, it whips around there very quickly. Well, a couple reasons for that. One, if you imagine that as like a tiny part of the circle, again, we're in an ellipse, but if that's the tiny part of the circle, well, what is really large at that point closest to the sun? Gravity. Because my radius is much shorter, gravity has shot way up because the two masses didn't change, radius went up, therefore, excuse me, radius went down, therefore gravity went up, that force. Now, you also notice that velocity increases dramatically right here, but is very low out here. Now, why is that? Well, if you think about it in terms of energy, and you look at the equation for gravitational potential energy, whenever you're close to a planet, whenever you're close to the surface, potential energy is just mgh. But whenever you get further away from that planet, the further and further out you go, the more g, 9.8 or whatever the planet is, the more that changes. So whenever we're dealing with planets and orbits and things far off, we use this equation, g m1 m2 all divided by r. And again, that r is the distance between the two objects' centers. Now, this negative is because we say that UG equals 0 only when R equals infinity. Now, we'll always have an R that is less than infinity, which means we have a UG that is always less than 0 or negative. Okay, so let's look at an example here with and let's do it with our solar system here. So I launched it with an initial velocity of 50. So if I kind of retrace out my orbit here, okay, there's the sun, and then here's my planet. At this point, I'll call that V1. I'm at a certain distance, which is R1. And then right here, I'm at another distance, which we'll call R2. And I'm at a new velocity here, v2. Okay. Now, at this point, over here, r is much larger than over here. So if r goes up, those two don't change. So if r increases, then the number that this term has decreases, but it decreases negatively, which means if you think about a number line, and there's 0, you are getting closer to that 0, which means your potential energy is actually increasing. So with a larger r, the more potential energy you have. The shorter your r, the less potential, which means the more kinetic you have. So we can utilize the conservation of energy for planetary motion. The only thing that's different, the only thing that changes between a problem like this and a problem where you've got a cart on a hill and it rolls down, blah, blah, blah. The only thing that changes is the fact that our potential energy is now not mgh, it's negative g m1 m2 over r. Okay, so I can cross off work, we can neglect any friction out here in our universe, and the kinetic energy is still just going to be k, or 1/2 m, we'll call this planet m1, and then our sun, we'll call it m2. So 1/2 m1, and then times v1 squared. Now it's going to be minus g m1 m2 over r1. So for my initial potential, if I use this point right here, the point where it's farthest away, as my initial side, well, I have to use that radius. Now, that equals 1/2 the mass of my planet, m1, and then v2 squared minus g m1 m2 all over r2. Now, if you look, what's in all of the terms? The mass of my orbiting body. And that seems to cancel most of the time, because when we were looking at circular motion, we said that gravity is the centripetal force. Well, break those apart, gravity, kind of scoot down here a little bit, there we go. And we'll come back to this conservation of energy here in just a second. But the force due to gravity was my centripetal force, which was g m, I'm going to go mc for the mass of the central object, and then ms for the mass of the satellite, all over r squared. That equals mac, and you always go the mass that's actually doing the accelerating, which would be the mass of the satellite, which cancels out. Now, AC is v squared over r. And so you can look and see, okay, if I get v by itself, in other words, if I multiply this side by r, well, I end up with g mc over r being equal to v squared. And that tells you right there what affects the velocity of a particular planet. It's the mass of the central object and how far away it is. So if I gave you a problem where you have Earth and then you've got all these different satellites at different distances, which one is going to be moving, say, the slowest? Well, the one that is furthest out, because they all have the same mc. But if r increases, velocity must decrease because those two are inversely related. Okay, now back to our conservation of energy up here. If I wanted to solve for this v2, this velocity right here at this point closest to my star, well, you would have to know, okay, velocity at some other point, the mass of what you're orbiting around, and the distances at each of those points. If you know all of those things, you can solve for that final velocity. So if you want to check and kind of do a problem here, you've got a distance over here, r1 of 200. So I'll go ahead and write these out for you. r1 is 200. The mass of your central object is also 200. So mc is 200. How handy is that? And remember, in our solar system simulator, g is actually 10,000, not 6.67 times 10 to the negative 11th. So r1 is 200, mc is 200, g is 10,000, and my initial velocity, or v1, was 50. So v1 was 50, and then r2, my point where I am closest to the star, is going to be, okay, that's interesting. There we go. R2 is 20, let's go with 30. So R2 is 30. And I want you to solve for that velocity at that closest point. And just so when you do this, you want to check and make sure that you're doing it right. Let me just kind of, oh, that is pretty close. You are going to get a velocity that is probably pretty darn close to 350. It'll actually probably be 355 or maybe 353 or so. So that's what you should get for V2. Okay. And again, you can work on that and solve that. So in summary, key to circular motion problems is first figuring out, okay, what is my centripetal force? Once you figure out what that is, you can start breaking the problem apart. So say you're dealing with a car on a track. The centripetal force is going to be static friction. Say you're dealing with a planet orbiting in a circle. Well, the centripetal force is going to be the force due to gravity. Say you're dealing with a pendulum, but that's moving in a circle, so a conical pendulum. Well, your centripetal force there is going to be Ftx. It's that tension force that's directed in towards that center. Because imagine that this pendulum is coming out of the board towards you and then coming in like that. So you could, I don't have anything on hand. I don't have my keys on the lanyard anywhere. But it's moving around in a circle like that. And so you've got that tension force at an angle. Well, you've got an Fty, which is canceling gravity. And you've got an Ftx, which is allowing it to move in a circle. And your circle is going to be flat like that. Now, remember, anytime an object no longer has, that circle was horrible, but anytime an object no longer has that centripetal force, it will leave with whatever velocity it had tangent to that path. So if you're dealing with a conical pendulum, it will leave as a horizontal projectile. If you're dealing with a car on a track and it encounters, say, an ice patch, it will leave. It won't skid, out some weird direction or anything like that. It will skid tangent to the path. And that's because you've lost that centripetal force. You've lost that force directed towards the center, which means you no longer have that, that acceleration directed towards the center. You just fly out straight. So that's what I've got for you. Be sure that you take a look at those problems that I suggested, and just study up and you'll be fine.